So yesterday we talked about the group analysis approaches available in Affinity. So for this section, we're going to using a few real data sets to try to use the programs to see how you feel about it. So the slides are under that directory. The hands-on, it's called Affinity 25 underscore group and underscore HO PDF. So the data is the same directory we have been using. It's Affinity data 6. So the subdirectory is called group and cases. So some of the Affinity programs, group analysis programs, are written in R. So you need, assume everybody has R already installed on your computer and the process of your packages. So this is just a review what we learned about the available Affinity group analysis programs. So we have 3D t-test++, 3D MIMA, then 3D MVM, and 3D LME. So in the future, we may have 3D SC, that's for inter-subject correlation, and 3D ICC, that's for intra-cross correlation. Then we have a couple of other programs or auxiliary programs. So I forgot to put the Bayesian approach here. That's I'm going to probably demo a little bit to use that program to run RI-based group analysis. The Affinity style programming, usually we write the scripts. So that's scripting is always sometimes a little bit challenging. Easy to make mistakes. So one common error is that we tend to forget to put either forget to put a backslash at the end of each line, or put some extra spaces after the backslash. Because backslash means you tell the program to continue to the next line. So that's basically a continuation character. So if you put an extra space after the backslash, then the shell will interpret that as the end of the current line. You will not continue to read the next line. So that would cause some trouble. So there's a tool Rick wrote to help to diagnose some of the common problems. So the program is a shell script program called file_tool. So you can use that to help you diagnose some of the problems, like extra spaces after the backslash. So the next few slides, basically, it's copied from the group analysis talk. So one thing, this one I want to mention about is about the R notations, which are typically used in both 3D MVM and the 3D ME. So the notation of A star B, that's the R notation. So when you have two variables, those variables can be factors or can be a quantitative covariant. So A star B basically means A plus B plus A colon B. So that means we have those two variables. We want their main effects plus their interaction. So A colon B, that means the interaction between the two variables. So A plus B, that means basically it's main effects without interaction. A colon B, that's the interaction. So that's for the fixed effects. For random effects, the typical ones, we want to tilt 1. Tilt basically means it's approximately, so that's what we want, random intercept. Tilt X, we want both intercept and slope. So the next few slides, basically it's the same as we saw yesterday in the talk. So I put those slides there just to help you to navigate the programs and those what scenarios you would of data structure you would which programs you would use. So now this is we have probably about 6 examples we're going to go through. So I think the first one is the case we have 3 conditions. So just one group of subjects, 3 conditions. It's an MEG data set. So 3 conditions. So it's a within subject one-way ANOVA, if we can conceptualize as the one-way within subject ANOVA, or repeated measures ANOVA. So that that factor is the condition. We have 3 conditions, 3 levels. So there's baseline, ketamine, and the placebo. One group of subjects, so that's 17 subjects, So the special thing about this case is we have some missing data. As you can see on the right-hand side, it lists the data structure. So depends on which condition, we have some of the subjects don't have data available. So it's typical when we have a longitudinal study. Right? So for example, for the baseline condition, the subject number 12 does not have data. For the ketamine, but actually all subjects do have data. But the placebo part, we have 1, 2, 3, 4 subjects have missing data. So what can we do when we have missing data? There are 3 separate approaches. The one approach, if we just stick with the traditional ANOVA data structure, then we'll have to remove 6 subjects because actually there are 6 subjects have missing data. So that's probably the worst approach. We have to waste those 6 subjects. We have to sacrifice them. So that's the first ANOVA approach. Or you can do a pairwise comparison instead of doing ANOVA. I mean, ANOVA doesn't gain much, except the only unique thing about the ANOVA, you are going to get the main effect of the 3 conditions. The main effect, I mean, some people call it omnibus F-test. That basically tells us whether there are differences across those 3 conditions. That's nice, giving us some summary about the 3 conditions, but it doesn't tell us where those conditions are. Like it says some differences across the 3 conditions. Those differences can be between the baseline and the ketamine, or between the baseline and the placebo, or between ketamine and the placebo. So we don't know where they are. So we still have to go through those pairwise comparisons. So instead of running ANOVA, we could just run 3 separate paired t-tests. So 3 conditions, you should pair up. Then you have 3 separately paired t-tests. So alternatively, we could run 3 paired t-tests. If we do that, that would be better actually in this case than the ANOVA, because each pair we only need to miss a couple of subjects. For example, between baseline and ketamine, only need to remove subject 12 and subject 15, right? So that's definitely better than the ANOVA approach. The third approach is we don't need to waste any information. So even for those 6 subjects with the missing data, we can still take advantage of the data available among those 6 subjects. So that approach is a linear mixed effects modeling. So that's the approach. That's the approach we're going to try here to demo here. So let's go to the terminal. Let me shrink and make it bigger. So go to the affinity data 6. Once we're there, we go to this directory. It's called group and cases. So all those hands-on examples are under that directory. So let's go to group and cases. Once there, now we'll go to the first example. Just type 1, then hit the tab key, then it will automatically complete the rest of the directory. So we go there, then you would see you have the data data directory plus a couple of scripts. So I already created the scripts there. So if you open the file, first there are some comments shows the data availability information, basically tells us what data we have. So in one group with 17 subjects, 3 conditions, then we have 6 subjects, we have missing data. So down below is the script, 3D RME script. So it's pretty much similar to what we saw yesterday with a 3D MVM example. So before I talk about the script, let's just run it on our computer. So if you have a TC shell, then we can just type TC shell, then RME text, right? So hit return. So let's try that, because it may take a few minutes. That's why I want we do that, then while you do, the computer works on, running. It doesn't work on my computer because I already have the output file available on my computer. But that's not the case for you. So you should run the script and see how it goes. So let me talk about the script itself. So this is pretty much like a 3D MEM. So at the bottom of the script, it's a data table. So if you're familiar with R, that's a typical R. The term is called a data frame. So you should have multiple columns. Each row corresponds to one data point. Right? In this case, it's one three-dimensional volume data, one brain. So the first column is always subject, so it's fixed. So you list all the subject labels. The last column is the input files. So the input files they don't have to be in the current directory. As long as you specify the path, you can put it anywhere. Can be anywhere, as long as you put the directory, the path that points to the input files. So the last column is the input files. Between the first and the last columns are all the variables. In this case, we only have one, which is the condition, right? The one factor is condition with three levels: baseline, k-mean, and perceivable. So that's basically the data frame, data table. Nothing fancy about that. So then at the beginning, we have this the program name, 3D MEE. Then the prefix, we use that option to specify the output file name. Then number of jobs. So on my laptop, I only have 2 processors. So that's why I'm specifying the number of jobs with number 2. The next line, the model. The model in this case is just one variable, just condition, which is the second column in the data table. The next line, SS type, that's the sum of squares type. If you are familiar with SAS or SPSS, you may have heard the different types of sum of squares, right? So there are 3 types: type 1, type 2, and type 3. Here we have type 1 and type 3 available. The popular one is called type 3. So you may wonder what they are and what's the differences among those types. This is something controversial in this among statisticians. What they mean is that there are different ways to measure the contribution of each variable in the model. So type 3 is the name is called marginal effect. So suppose you have multiple variables. Each variable may make contributions to the data variability. So marginal effect, that means you put all the other variables in the model first. So this variable would be the last one entering into the model. So that's why it's the marginal. So you already explain everything else first. Each variable's unique contribution would be the extra one, would be the last one. So you let everything else, all the other variables, take whatever they could first. Then you measure the unique contribution by putting that variables as the last item coming into the model. So that's called a marginal effect, yes.
So do you have a list of these commands? Maybe it's syntax error now, not one behind them. Like I typed one thing wrong and I thought I have an error saying the data table is not rectangular. Is a list of the commands you just went through on PDF somewhere? Or did you walk through it?
Walk through what?
You typed the command and I must have typed it wrong.
Oh, okay. Okay. See,
I have the right file. I just typed it.
so I type tssh lme.txt. Is that? So that's the concept of sum of squares, different types. So there's type 3 means it's a marginal effect. Type 1 is called sequential. So that means it's sensitive to the order. Basically, you as a user, you specify the order of the variables. So it would be the order will decide how much contribution each variable is. So the first variable in the model would take as much as it could, then you move to the next. So that's, people don't like that. Some people like that, some people don't, because it depends on where you put it where the order in the model, then you may have different result. So, but that's, we have type 1, type 3 available in 3D-RME. So the next line is the random effects specification. In this case, since there's only one variable, the random effect specification is pretty simple, just random intercept. The next line tells the program there are how many number of general leader tests, GOT, general leader tests. So we wanted 5. So each line specifies the test, post-hoc test we want. So the first one, general GOT label, let's just use that to specify what this test is about. So in this case, we want the ketamine condition. So remember, there's just one variable condition. There are 3 levels for this variable, this factor. So GOT code, we use that option to specify what the code, what exactly we want. So that we put in within quotes. Condition is the variable name. It's a factor, then space, colon, space. Then 1, that's the weight. Star, that means that weight applies to that level. So in this case, it's the ketamine level, the first level. So the first post-hoc test is pretty simple. The second one is a contrast between ketamine and placebo. So you can see now we have 2 weights, 1 and -1. Then basically we compare the 2 conditions. Right. So the next line, I mean, it may not be meaningful. I just wanted to use that to demo what kind of weighting we can do. So in this case, we want the ketamine minus placebo and minus baseline. Right. So there are 3 weights. We put basically compare ketamine versus the sum of placebo and baseline. Any questions about the post-hoc test? So it's similar to the symbolic coding in 3D deconvolve in affinity product.py. It's similar. So that's what this program does. I mean, what this script means. For those of you who already got the result, so we can look at the result, right? So, so launch affinity. So on the terminal, well, actually, the output file probably is called RME something, RME. Yeah, for me it's called a condition count.rme2. I mean, yours perhaps something similar. So that's the output. So on the terminal, let's type affinity, launch the GUI, then look at the result. So I don't have an anatomic data set here, so that's why you see the underlay, it's a little bit fuzzy, right? So this is not the anatomic data. It's basically the output actually from 3D-RME. So that's underlay. Overlay is already loaded because that's the only 3-dimensional data set available. So let's look at here. So I mean, at this point, I think everybody is familiar with the affinity interface. So underlay, we don't have the anatomic data set, but we just leave as using the output as the underlay. So this overlay, for example, we want to look at, for example, the subject number 4, which is the contrast between ketamine and the placebo, right? So that's the overlay. Then threshold, we use the t-test. In this case, it's a z-score, z statistic. It's a Gaussian test instead of a t. You may wonder why it's z statistic, not t. That's because for 3D-RME, some of the test is, we don't have the t-test available, so we convert to z-score. I mean z-statistic. So we need to change the range of the threshold bar because by default it's always from 0 to 1. In this case, z is pretty much like t. We want to change the range, so we switch this order 10 to the power of 1 instead of 10 to the power of 0. So now let's navigate, move this threshold bar down to something reasonable number, like 2 point something. Now you will see some colored blobs, clusters. Right? Yeah. Yeah.
I've got all the same stuff to do, but I have a black background instead of a white background.
Oh, I changed my default, my setting.
Okay.
Yours is the real one. Usually I don't like the black background.
Okay.
I think there's an option that allows you to. Yeah, I don't remember where, but if you like it, I can tell you later on what change you need to make to get that. I mean, especially when I save the images to put in the paper, I don't like the background. When people print out, they print waste a lot of ink. You may notice, as I mentioned yesterday, under this threshold bar, there's a p value there, and also there's a q value. Do you remember what that q value is about? It's the FDR, first discovery rate, right? So that's automatically, you can use that as a one way to handle multiple testing correction. So if you're happy with result, but in this case, there's a lot going on in the brain. So if you read the Q doesn't change much actually. So you can see here the F discovery rate is truly conservative, especially for this data set. One more thing I want to mention here is, usually it's reasonable to adopt two-sided or two-tailed testing, right? We keep arguing that, but even though in the field, everybody else uses one-tailed test. That kind of problematic unless you have prior assumption about the directionality of each effect. Otherwise, people just keep doing paired of one-sided tests. Automatically you have multiple comparison issue. You should adjust the p-values. Nobody does that. So that basically cause you automatically inflated your false positive rate. So that's problematic. But if you can justify your one-tailed testing, you can do that indefinitely, even though the default, what you're seeing on the screen right now, the p-value under the threshold bar is it's two-tailed. But if you can justify your choice, you can switch to one-tailed. How can you do that? You can use your right mouse button by putting the cursor to the top of the threshold bar, then hold down the right mouse button, then you bring up this menu. On that menu, there's a sign. Currently, you can see pass and neg, positive and negative both. So that's two-tailed, right? Anybody has trouble, have trouble get that menu? So you go to the top of the threshold bar here, then then hit the right mouse button, hold there. That brings up another menu. On that menu, you say this at the middle of that menu, you say sign. It says both plus and negative. So if you use your left mouse button, you can choose positive only or negative only. So in this case, suppose I want to choose positive only. So now the blue, those negatives are gone, are hidden, and the p-value changed. The p-value suddenly divided by 2. That's because before it was two-tailed. That means the sum area of the two tails add up. Now I just focus on the positive, on the right-hand side, there's a positive 1. So that's why the p-value by 2 now. Okay. So you can do the same thing for the negative 1. So you go there, then I change that to negative only. So now on the screen you see the blue ones. You don't see the orange clusters. So that's how you deal with switch different directions. I think that's this a simple test. It's just data structure is pretty straightforward. It's one factor with 3 levels. It's typically this would be when we repeat measures ANOVA, but because of the missing data, we're using linear mixed effects modeling approach to handle the situation. Now let's switch to the second example. One directory up, go to the second one, 2.3 groups. So in this case, we have 3 groups, right? So there are many ways. Here I put 5 different ways to handle the situation. But now let's look at the number 5, the last one. So 3 groups, that means it's a one-way between subjects ANOVA, right? Plus a covariant. So this would be an ANCOVA actually. So anybody has trouble getting to the directory? So you go one way up from the previous directory, so it's 2.3 groups. So once you have multiple script, so we can run the script by typing tssh 5, number 5, type that, then that would run 3D MVM. Okay, hit return. I have this rectangular. That's probably, I don't know if you have this problem. I'm not so sure why this, I have to take a look. Probably changes something recently. You don't? Huh, okay, all right. What is 4? 4, oh, okay, the 4 is not MVM. But anyway, that's, well, then you just have to listen to me then. This is, remember, there's 3 groups. Whoops, what's going on here? 3 groups. There's 3 genotypes, actually. There are homozygotes, there's a heterozygote group, so 2 homozygote group. So there are 3 subjects for the first group, 10 subjects for the second group, 9 subjects for the third group. So 3 genotype groups. So there are unequal number of subjects across the 3 groups. That's not a big deal. But the thing here, we have a covariant, right? So which is the FD. So that's I forget what that is actually. Some quantitative measurement for each subject. So at the bottom, it's pretty much like the previous linear mixed effects modeling 3D RME. We have this data table. The data table, remember, first column is always subject labels. Last column is the input files. So you notice that the data is put in the subdirectory, data directory. Each input file, we use the subject selector, use the label to choose which subject we want to use as an input file. So between the first and last columns, they are all the variables we want to consider. So the last column basically is the Y, the response variable. Between the last and the first and the last columns are those the explanatory variables. So one thing I want to mention that you can put a table, but you don't have to use columns in your model. So that, for example, here we have 2 columns in between, but you could put other variables which you don't have to use in your model. So that would allow you create one table, you can change your different models, you can try that. So here we basically columns, 2 explanatory variables. First one is the group. So we have 3 groups, right? So the 2 homozygote groups plus the heterozygote group. Then we have the covariant, FD, that's quantitative covariant. So that's the data structure we have. Then the first line on the script is program name, 3D MVM. So we use the multivariate modeling approach to handle this ANCOVA structure, right? So we don't use, in FNA, we don't use the univariate general linear model because that approach is very limited and people don't do it, its capability limited, and if you don't do it carefully, you may get wrong results as what's going on in the current other software packages. So then you use prefix to specify the output file. Then again, we use jobs option to run parallelization. So the next line is the next 2 lines are different from 3D RME in a sense. we don't directly specify the model. Instead, we specify the model, the variable types. So BS vars, that's between subjects variables. So in this case, we have two. Group, then we have the FD value. So we put a star between the two variables. That means we want both main effects and the interaction between the two variables. So in this case, the two variables, one is the factor, one is the covariant. So the next line, it's Q vars. Q means, so we need to tell the program FD is not a categorical variable, instead it's a quantitative variable. If you don't do that, the program will treat FD as a factor, then that would be totally, would mess up the analysis. So we basically use those two lines to specify the variable types. Then there's the issue of centering, right? Since we have a quantitative variable, do we need to do centering? If we don't say anything, don't use, there's an option called Q centers, Q vars centers. If we don't use that option, the program automatically center around the mean across all the three groups. So, but in this case, I already centered within each group. So I did within group centering instead of overall centering. So that's why I didn't specify it. I didn't specifically add the option there to tell the program to remove the center. So the next few lines basically specify the post hoc tests. So for example, the first one, we want the contrast between those two genotypes, right? So the coding, we just put the weights in front of each factor level. So either 1 or -1 typically. The third one I want to mention is that remember we have two variables. One is genotype, the other group. The other one is the quantitative covariant. So we can the third line is a little bit different from the typical post hoc test. We want the covariance effect. So you say the variable name space colon. That's it. That means we want to say the quantitative effect, the slope. So the next two lines are pretty much similar, except we want to test the FD effect. Say the FD effect, the difference between the two groups. So we want the slope differences between those two groups. That's the script for 3D MVM. So then, I mean, there's an alternative approach to write the script. You don't have to write it. You can use, let me see if I have it here. You can use, there's a Shiny program Justin Rojandro wrote recently that can use the GUI to write the 3D MVM script. So how can we do that? There's a web page. I think he set it up. So let me start from the beginning. So usually, I mean, you can start from anywhere on the web page. So for example, we start from the message board. So you click this documentation, that tab. So once you are on that page, I think you go to the number 8.11, this one, 3D MVM validator. I think, at least I hope he will write one for 3D RME as well later on, but we're still testing this one. So this 8.11, that's a 3D MVM validator. So that's web page specific is devoted for this script generator. So you can read this. I mean, follow the instruction there. But here I just want to demonstrate a little bit. Where's that? I think he mentioned somewhere. It's not it. Oh, here. Basically, on the terminal, you just what you need to do is you have to create a table. That part, the GUI does not help you. So you have to create this table. Basically, that's at the bottom of either 3D RME or 3D MVM data table. So that table, as I mentioned several times already, the first column is always subject labels. last column is the input files. In between, you list all your variables. In this case, we have the group, 3 groups. The second variable is the quantitative covariance. So you create this table. Once you have this table on the terminal, you type this command: 3D MVM underscore validator dash data table. Then put the name of the file name of the data table you created. So then you hit enter. So now what it does is going to check whether you have all the R packages installed, then launch Affinity, then load up one data from the list of the last column from the input files. And also you will launch the validator on your browser, automatically open your browser, then load up this page. So on the Affinity here, in this case, you may wonder why it's not a brain, because in this data set, I simplified it just, I believe it's just 3 by 3 by 3, 7 voxels instead of a whole brain. That's just for demo purpose. So on the browser, there are 3 steps. On the left panel, there are 3 steps. So you need the first one, get your coordinates. That means the reason we want to get 1 voxel surface 1 node is that we want to test your model before we run the whole thing. So whether the model works or not. So that's why we need the, move to the, okay. So first we go to the Affinity interface, go to one of the 3 panels, then pick 1 voxel. Suppose I pick the one in the middle. So you have to watch me. You don't have probably you don't have the table created on your in that direction on the computer. I forgot to do that this time, but next time I will do it. So click on one of the on the 2-dimensional panel. You click 1 voxel, then you say I get the coordinates for that voxel. So on the panel here you will show the coordinates, right? The coordinates the X, Y, Z, or it depends on it's RAI, PI, or IJK, so it shows up. So it shows the location of that voxel. On the lower right corner, it will show it's successfully loaded, found that voxel. If there's something wrong, this would be red. So this first step, we get 1 voxel for model testing purpose. Then you would, well, in this case, it's RI. It's a voxel instead of RI. So next step, extract the data from that voxel. So you may notice the lower right corner will tell you if there's something wrong or it's successful. So in this case, it's already loaded the data. So that's the second step. The third step on the left panel is we load the data. So we load the data. So once we have the data, so now we start to work part, modeling testing. So on the top, it automatically detects how many variables we have, because it just reads the table, right? So it's like R, you read the data frame. So it tells us there's a group variable, there's the quantitative variable is FD. It automatically tells us, it's a numerical variable, or whether it's a numerical or categorical. Down below, so here, specify between subjects model, variables. We have the group, automatically put it there. Then specify within subject variables. We don't have, so both variables are between subjects. The next line, specify quantitative variables. So we need this, FD is a quantitative variable. So basically we do that. So it automatically updates once you type in the variable name. By centering, well, in this case, it's already centered, so we don't need to do anything. So at the bottom, it shows the modeling result of the current model. We haven't fully specified the model yet. So at this line, I need to put the FD there. So once I do that, automatically updates the model. See, that's pretty much like an ANOVA output, right? So you have the two main effects, plus the interaction. It shows the degrees of freedom, shows the F statistic, shows the p-value for this particular voxel. So model part. So then we need that would only give you the main effects and the interactions. So now we need to do something about the post-hoc test, right? So we click this tab, GLTs. So we put a label. Suppose we want the contrast between the two genotype groups. So variable name, that's group. Then specify the levels. So suppose we want to compare V versus VM. So we choose those two. Then we put the weights, 1 and -1. So add variables. So then it automatically generates the coding as we saw before in the 3D MVM script. So once we have that, then we just add the GOT in. Once we have it in, so we can check the script. So now at the bottom, you can see that's pretty much what the script I wrote myself. So right now I just specify the one, I probably failed to add the GOT, but let me see why it's failed. Oh, it didn't, for some reason it didn't work. But anyway. Okay, I forgot to test. So now test it shows that for that post-hoc test, now I can add. So once I add there, then go back to the script, then we see the general linear test is added to the 3D MVM script. So that's the 3D MVM valid. So you can use that to create a script if you, especially for the beginners, probably maybe it's a good idea to use. So then later on, you may just write yourself without using the validator. But it is a good idea, not just the script itself. It also allows you to test whether the model is a reasonable model. If something wrong, you can immediately to figure out instead of run the whole analysis on the whole brain, right? So that it is nice for the model testing purpose, not just the scripting. Any questions about this? About the script and also the validator?